Welcome to lecture number 10. In the previous lecture we saw the FACTS controllers, that is SVC and STATCOM only, although we will see some more FACTS controller in the next module. In this lecture number 10 I will be discussing that which I said in the lecture number 9, that the shunt controllers, they will improve your steady state limit, that will improve your transient stability limit, that will improve your voltage stability limit, and that will also damp out the power system oscillations. So all these four advantages with this shunt compensation, that is shunt FACTS controller, will do it. We will see how they are going to how they are going to change the limits by controlling these values. To understand this, let us start from the very basic. Very basic means, if you remember here we are having, let's suppose, two systems. This is one system, this is another system, and that is connected by a transmission line that is having the reactance X. Now this reactance is divided into the two parts. I want to show you, if we are going to put here in the middle of that transmission line, so that's why I have put the reactances half at the both sides of this midpoint Vm, and it is connected by, that is a total reactance of the line. I am ignoring the losses, that is the resistance of the line, and this system is angle, it is 0, and we are having the angular separation between these two is your delta. Now if you write the power flow from here, from this, that is your P and Q, we will get, as already I have derived here, that P will be V1 V2 upon X sin delta, that is the angle difference between these two buses, and X is the total reactance of this line. If V1 and V2 are equal, let's suppose we are maintaining the voltages 1 per unit are equal, then it is a V square upon X sin delta, and the corresponding, the P delta curve, that is here P, and this is your delta curve, we will get with this curve here, that's I have shown it to you. And we know that maximum P max, that is we can get here at the angle pi by 2, that is a 90 degree, means if you are here putting the delta is pi by 2, this will become unity, and we will get the P max is nothing but your V square upon X, and that we are getting delta is equal to pi by 2, which I have shown here. For the reactive power, here in this expression, you can see again, you can put your V1, V2, both are equal in magnitude. So we can get here, and then your the curve for the Q here will be this dash line, and you can see here. Means at pi we are getting the 2P max. Means you can put here delta is equal to pi in the above equation. You are going to get here V square upon X 1 minus 1 means here 2V square upon X, it means here 2P max. So you are going here the double of this value here, this P max, here also we are getting P max. Now how we got it? It's very simple. Means simply the power here, that's S, that flowing from here to here, I can write simply the voltage into the current conjugate that is flowing here, and the current conjugate here, what is this voltage here? This is a V2. Now I can say angle, these are the vectors, angle delta. Here this I conjugate is the basically the voltage, this minus this, means I can write the V2 angle delta minus V1 angle 0 divided by your Jx, and this is the conjugate. So if you are going for the real and reactive parts separately, for this case, let us put V1 is equal to your V2. You will get the previous equation. From here, this is nothing but your P plus JQ. So you can separate out real and reactive powers here from this expression. We will get, of course, your P will be your V1 V2 upon X sin delta as the previous case, and Q will get here this expression. So it is very simple, there is no need to remember, you can derive also, and we can have these characteristics. Now Now let us see what is the voltage at this point. Means if you keep on increasing the loading, means if delta is increasing here, what will be the midpoint voltage here? To see this, the midpoint voltage, it is nothing but, can be calculated here. Now the power which is flowing over this section will be equal to this section. Means I can write here, this is your Vm, V upon x by 2 sine delta by 2 will be equal to, that is equal to your P, or this P which is flowing here, I can say V square upon x sine delta. Means I can write this Vm will be nothing but your V cos delta by 2. Means you can just obtain from this equation. Means here VV will cancel, x will be cancelled. Here sine delta I can break into the two terms, that is a sine delta by 2 here twice into cos delta by 2. So sine delta will be cancelled and here 2 will be also cancelled. So we will get here this expression. And if you are just going to draw the graph for this, what we are going to get, we will get this V cos delta by 2. Means here if you are going to draw this, I am drawing here your midpoint voltage Vm, this is your angle delta. Now and I am going to draw this Vm, it is nothing but your V cos delta by 2. When delta is 0, V is your the value, that is a 1 per unit here, that I can say this is 1, or you can say V here simply. When delta is 0, when delta is your pi by 2, what will happen? This will be value, means pi by 2, means it is a pi by 4, means it is your V into cos pi upon 4, means you can say V upon under root 2, means we are getting some voltage here. And when delta is pi here, this is a pi, so this is 0 and we are getting 0, so we are just going to get this voltage profile, and this voltage is nothing but your 0.707 V. So it is saying when you are achieving here, the voltage of midpoint is going to be 0, and this is the decline in the voltage of this one. Now if we can maintain the midpoint voltage to its 1 per unit limit, then we can see we can transfer huge amount of power. So this is the limitation. So once you are throwing more power means more delta separation. So you can see the voltage angle here, the voltage magnitude of your this bus, that midpoint is decreasing. Now what I am going to do, if let us we are maintaining that voltage here, which I said this voltage if you are maintaining to V by any device here, means I want to put some device here, and that is your FATS controller. It may be your SBC or STATCOM. With that we can maintain this voltage by varying this XC or injecting some reactive power to the system. Means we are maintaining the Vm voltage to the V, and let us see what is the improvement, what next we are going to achieve. To see this, what we are going to have now, in the midpoint voltage is your no doubt V. Now I can again write here, this is your generator, this is your transmission line, this is your midpoint voltage, here this is another transmission line, and here we are having another voltage source, here V angle 0, here we are having V angle delta. This voltage we are going to have a V angle delta by 2. This is a midpoint, so the delta will be shared half of that. So this your midpoint voltage magnitude, just we are fixing to V, but angle will be half, and this value is your nothing but x by 2, this is also x by 2, and now we want to derive the power. So the power which will be flowing here, it will be the P, your V, any section, the power here will be equal to the power here. So either you can write for this section or this section, immaterial. Let us write the power for this section, that is between this voltage and this voltage. So I can write this here, the V square upon x by 2, this section, into sine delta by 2, or I can write here 2V square upon x sine delta by 2. So now this is the power flow which is flowing this expression, and this expression if we will draw the characteristic, what is happening? If delta is 0, this P is 0, we are here. If delta is pi by 2, then this is your, what is happening? This value is your pi by 2, you can put 2v square upon x, here pi by 4, 1 upon under root 2, so we are getting under root 2 v square upon x, and we are getting some value here, that is 1.4 times here and this value. When it is pi, this value is unity, and then your this p will be your twice v square upon x, it is at delta upon delta is equal to pi. So this shows that now this is a twice p max, and we are going to here, and we are now, this is the characteristic if we can maintain the midpoint voltage. Now what is happening? You can see here there was some stability problem here, means it was not possible to load the power system, the system more than this 90 angle, that's pi by 2. Even always we load below this because there is some surge or transient, system will lead it into the unstable zone. So we can go maximum in steady state up to this point. Now we can go the twice of that, and here all the region is stable, here it was not stable even though beyond this. So we can see we can have increased the steady state voltage, steady state limit, power transfer limit of the system to the twice of the P max value. So it is increased. Now you can see the reactive power, this Q, what will be this under this condition? It will be nothing but that is your 4 V square, you can derive it, x, and it is your 1 minus cos delta by 2. And now what you can do, you can draw the equation here, and it will be like here, and this is your Q will be appearing like this. So here I want to tell you that by this maintaining the voltage, now what will be the mid-time voltage? Thus we are maintaining to the V, the constant. So if you are maintaining the voltages in the transmission line at the equal interval, what will happen? We can transmit more power. So this is the beauty of your FACTS controller, and then I can see here your steady state limit is improved. Now other, just I can again explain you that how the voltage stability that can be improved. Let us see that. To see that, now I can draw here the PV curve, that is very widely used. We use the P delta curve to see this steady state limit. Now I am using the P power which we are flowing, and this is your voltage of that load. Now what we are doing, now you are very well aware that the PV curve is this much, and the maximum you can go up to this loading of the system, and this is called your nose point. Already I have explained in the voltage stability. Now if you are going to use the compensators, means for your, let's suppose you are having a generator, here your transmission line, this is your load, and if you are using some compensator here, that is a shunt compensator, again it may be your SVC or STATCOM here, that is a variable. So we can here, that is a P that we are drawing here, and the voltage at this bus we can maintain it. So here with the help of, let's suppose you are just going for the leading here, if you are injecting reactive power, your this value will be like this, and it may be sometimes like this, it may be going this. So this is leading power factor. If your lagging power factor here you are observing, then you can go for less loading. So here it is lagging, and this side this is a UPF, I can say unity power factor, and then we can improve, we can say by providing the reactive power support, we can go for more loading here in the system, and then we can go for the voltage, more voltage stability limit of the system. So here with the help of shunt compensator, we can improve the voltage stability limit as well, which I explained you in shunt compensator. Now another, just I am going to discuss about the transient stability limit, and let us see how it is going to improve the transient stability limit. Again we will consider the same system, that is we are having here, that is a line that is a partition into two part, here the volt, that is the source, here another source, and we are having here the midpoint voltage, that is your x by 2, here x by 2, and this voltage is angle delta, here this is your angle 0. Here we are putting some compensator in the mid of the line. No doubt this compensator can be put anywhere, but if you are putting the mid, just I have explained the whole theory behind that. You can put somewhere and again there will be improvement of course, but it may be the better improvement if you are putting in the mid of the line. Now what will happen for this case? Now let us draw here again the P. For the transient stability always it is an angle, here it is your power angle normally we discuss. So this is your P delta curve, let us suppose in the normal case. Now I said that it is, if we are going for the midpoint compensator, here our the characteristic is going to be here double of this. So this is your, when we are putting the compensator and we are trying to maintain the midpoint voltage to the sending end voltage from the fixed voltage. Now if there is a fault here at the bus, let's suppose your system was operating here and there was a fault and the power injected to this system is 0, this machine will accelerate, this machine will accelerate, and then here what happened, this was your PM, now your fault is, let's suppose it was operating at 0 naught and the fault is cleared here at this point, that's delta 1. Suddenly what will happen, once fault is cleared, this will follow this curve and it will see that your mechanical power which is flowing here is more than your electrical power and machine will decelerate, and then it will try to decelerate up to certain extent and here it will be this area. So area here is called accelerating area A1. This is your area that is called decelerating area A2. So this will go up to that point when it will be equal to this, and then if this area is equal, now we have this margin up to this value, means this machine can decelerate up to this point, otherwise again it will start accelerating, because here the P mechanical is at this point, P mechanical will be more and machine will more accelerating. Here PE curve, this P electrical, this delta is basically P curve, the P delta which I am drawing, it is the electrical power that we are drawing. So this is basically the margin we have. Now you can see if you are having the compensator, this I explained without the compensator. Now if you are again operating here, there was some fault here, three-phase fault, system was cleared, let's suppose the delta. Now here you can say we are going to up to this point, and now this area we require only this much, and this is your decelerating area because this area must be equal. Now the margin, you can see we have the margin here up to this point, this is your margin. Now you can see huge margin we are having. Earlier we had this margin, you see this margin we had, now we have a huge margin. So it shows that your transient stability limit is improved, means you are having a larger margin. Normally this characteristic is very ideal, means it is assumed that this compensator is having infinite power, which is not true. So if we are having some sort of, let's suppose we are having some limitation on this in reactive power, it may be going up to this and again it is coming here. It may coming here again for the different value of x's. Means if it is not infinite, so once it will be hitting limit, it will go to the 0. In that case also, you can see now this margin is now changed here and still it is more than the previous one which was here. So we can say the system transient stability improvement is tremendous if you are putting some shunt compensator. And I showed you the margin is more, means more you are stable, even though you can go for the more fault here, and even though fault is persisting for longer period, your system will be not unstable. If margin is less, there will be chances your system will be unstable because you will not have the enough margin and system will keep on oscillating and delta will be keep on separating from other machines. So similarly we can also explain, let's suppose our system here is a generator which is feeding and connected with the two lines. Let's suppose we are putting here compensator and here is infinite bus, and again we can now show for the other conditions, other system, here it was single line, now we are having the two lines and fault occurs here, we can show again the transient stability limit will be improved significantly. Means here what will happen, now this is again your P delta curve, that is called post disturbance fault. In the pre-disturbance, before that, we had this much. during the fault we can say this one. So this is your during fault, this one is your post disturbance fault, and this is your pre-disturbance fault. Why pre-disturbance condition? Because the system was in healthy. Here when there was a fault, this machine was oscillating and we had this characteristic. Then this line is tripped, impedance of this line is more than the previous one, and then we are having this line. Now let us suppose we are operating here. What happens during this? The system came here, it was going up to this period, and again this was during the transmission line is tripped and machine is oscillating here. So you can see this area here should be equal to the area here, and we are having this margin. Now if you are using the midpoint compensator, this is the case when there is no compensator. If you are using the midpoint compensator, what will happen? In this case also, here now this will be improved, this condition we can go for the larger value, and now you can say we can have the larger margin here. Even though outage of this, we can improve this. So the margin here again, that is a increase. Now another, I said the advantage of shunt compensators are here, I can say it is the power oscillation damping. In underdamped power system, any minor disturbance or small disturbance can cause machine to oscillate around its steady state value at the natural frequency of the total electromechanical system, and that is called your power oscillation. The lack of sufficient damping is a major problem. Means if you are having less damping in the system, then this is the major concern, means oscillation will persist, even though sometimes if your damping is negative, your oscillation will keep on increasing, and that will lead to your power system chaos, and that will give you other problems. So the shunt compensators can be applied to counteract the oscillating and the de-oscillating swings of disturbed machine. When machine will be oscillating, as I said, here you remember that is your h d squared delta upon dt. Here it is your Pm minus Pe. Basically it was here pi f, and then we can write this machine. So this is your oscillating power, machine will oscillate if your Pm is more than P. If Pm is less than P, then machine will de-oscillate. So what happens, the power swing here normally of this characteristic, this is, let's suppose your power is oscillating, this is, let's suppose the power, and it started oscillating here. This was your P naught, and this is your with respect to time. So this is oscillating. Now what we can do, if we can do any some mechanism that reactive power support we can provide from this point, means here if the oscillating we can inject more reactive power in the system, then it will be, and if it is underdamped, then we can go for this. What will happen, this machine will be here and slowly, and this will be stabilized. So with help of reactive power injections, when it is oscillating and de-oscillating, means power is more or less, then this machine will be stabilized, and this will improve the power system damping, and then we can damp out this. Another, which I said, the natural frequency of the system. You know, here we are having the generator. This generator is rotated by the turbine several stages. So we are having several natural frequency of these systems. So there may be possibility these oscillations will interact with the natural frequency of the system, and the huge oscillation will occur, and sometimes it may give chaos, and you can say the damage of the equipment as well. So the swings of the disturbed machine, we can put some reactive power compensation. In this way we can damp out the power system oscillation, and this is another advantage of your shunt compensation. So that can be done by both SBC and STATCOM. Only the characteristic will be changing, and therefore they are having some advantage and disadvantage accordingly. So let us see how the current that will flow in the SBC. As I said, only the variable part that we are having here a thyristor, that is anti-parallel thyristors, and as again I have to draw here, and then we have one inductor, and then we are having other component, that is a capacitors. Now I want to draw the characteristic, if you are changing the firing angle delay angle, that is alpha here, then this is L, how this L is going to be changed. So let us take if the firing angle is 0, and then what I am going to draw, let us draw the sinusoidal curves here. Means here your IL that is flowing here, this is your IL current. Now the voltage will be, as I said, here it will be, the current will be lagging here and voltage will be leading. So I can draw here the 90 degree. So this is your, I can draw the voltage curve here. Again the magnitude will be the different, of course, and this is your voltage with the dotted line, that is a V. Now when this alpha is 0, then we will get the IL completely, because pure this L is appearing at this bus, and this alpha is 0, means they are just behaving as a short circuit in the both cycles. Now if you are delaying, what will happen after that delay? Here let's suppose this alpha is delayed here, the current which will be flowing, that is the conducting here for half of the period, and your current here will be this much, and this both side this alpha will be there, and this value is your sigma. So this is the case when we are just going to have, and what happens now, this value here which is appearing, that is your Vm over omega L. Now just I can write this expression here, as we know this L di by dt, it is nothing but your the V, and this IL, this inductive current in the time, I can say 1 over omega L. I can put here the differentiation of V d omega t. Now I just have changed the dt here. Now here again let's suppose we have the V as a Vm cos theta, means V, just we are applying your Vm cos omega t. So we can write 1 over omega L integration from alpha to omega t, just we are firing, that is your Vm here cos omega t d omega t, and finally here we can get 1 over, now Vm will be coming out omega L, and now here we can say sin omega t minus sin alpha. So this is your the current that is flowing here. We can just, there is some phase shift here and it is coming here, means when alpha is 0, means here the switches are closed, or you can say it is a short circuit condition. When alpha is pi by 2, then what will happen, then it is a open, and then at that case you can put this alpha is equal to pi by 2, we will find it is open circuit, and I can say OC will be there. So changing firing angle means the changing the impedance, and thus the Z here I can say it is nothing but V upon I, and since V is a constant and I is changing by alpha, so again I can say this ILF will be nothing but your Vm over omega L, here 1 minus twice pi upon alpha minus 1 upon pi sin twice alpha. Why this is a big expression? Because we are now talking about the fundamental component of this type of frequency here current. So here this is some repeated curve, so we can go for the fundamental component, and then we will get this LF will be this value. So we can get the impedance that is dependent on alpha. So once you are changing alpha, here your impedance is changing. So again we can put your this impedance Y is your I upon V, and then we can get the expression here. And now you can see this ILF, this is the fundamental component, how it is changing. If it is alpha, this is your ILF, this is the fundamental component of this current, inductor current. This current, just we have taken the fundamental component, harmonics let's suppose we are ignoring. So you can see it is starting from some value, if it is alpha is 0 from higher value, and then it is going to be some is at pi by 2 it is your 0, and this is your this value. Now what we are going to do in this one, we want to just, this is very important characteristic, and we'll see with the change of alpha will and other components here, because we are adding some capacitor, will have the different zones. There will be one portion where this X will be cancelling out with the other X, and then we'll have some resonance, or we can say margin, where we should skip from inductive operation to your capacitive operation. Means in this STATCOM we are going to add here this capacitor. So this is called, this is nothing but your thyristor controlled reactor, this unit, because the reactor here L value is controlled by thyristor, so it is a TCR, and here it is your fixed capacitor FC. So this SVC is nothing but your TCR, thyristor controlled reactor, plus your fixed capacitor unit, and then we have to see the characteristic of this whole system. Now we have to now go for the various characteristic using this IC and the BC. What we are going to do now, if you are connecting some here, some current is flowing I, and then we will see with the help of voltage and current we can have the different characteristic. Means let us a characteristic of this circuit we want to draw, then it will be more clear. So this is your thyristor unit, this is your inductor, and we have this. This is your, I can say this is a FC, this is your TCR, and some current here is flowing here I. In this, if it is IC here, so IC is nothing but the voltage multiplied by the BC. In this one, here what we are getting, so for this characteristic you can say if the BC is changing, the voltage here is a linear characteristic. So I can draw here in the one zone, this is your, let's suppose a current I. So this characteristic is the voltage, that is VC is inductive, that is the linear curve, and then we are getting here, and this is your capacitive, that is a IC. So in this zone, and we can go at certain value, that is your, this is the maximum IC max value, and this is your slope is BC. Similarly, here in the your inductive zone, in this one, we can also write what is the here BL, and we can say this IL is your V, that is a BL here, and this we can say now we are having another component here, that is your BL. So this is inductive. Now with the varying your this BL value, now if you are having the fixed reactor, let's suppose this is your C, this is your inductor, what will happen? We have to have a combined one. Then characteristic this and this characteristic will combine, we will get some characteristic, and this will be a point characteristic, line characteristic. But with this variability of this, we can have the zone controllability. Means if you are adding this, what will happen? Now there is no variable, we will have some characteristic either positive or negative, means either this zone, means suppose here, resultant may be somewhere here in the between. So your operating point will be the these with the different value of the VC. Means different value of current, if a voltage you are changing, the current will be changing. But here, since this is a variable, so this is the zone. So between this to this, means if this value is 0, we can go, we can achieve here up to this point. If this value is more, then we can go this side, and then this is your characteristic. So we are just getting a characteristic of inductive zone here, and the capacitive zone here, this we are getting this. So this is value of maximum BL max, BL here, and the current here we are, this is your BL max here, this maximum value we can achieve. This is slope to the boundary of the, because it's a variable. Inside this the total we can get, and the current which is we are getting here, that is IL max, that is the maximum current that can flow in the inductor. Now what we do, there is a possibility here, this is a characteristic here we can achieve, and normally we can say this is the characteristic here. We operate normally in the capacitive zone. When the voltage is less, we must operate in the capacitive zone, that we require the reactive power and we must supply it. So our characteristic here normally moves here and then slightly going here and then at this point. Means when the voltage here, the reference value is less, we have to operate in this zone because we have to provide this. If voltage is more, then we have to go this. Here this is very, if it is a straight line, what will happen? It is oscillating. So it will be moving, means what will be the current, whether it will be here, here, at which point if it is a slope. What we do, normally we provide some characteristic, and this is normally we have to go for some regulating slope we provide, means this is here, this is your inductive part, and we provide normally this some slope here. So the characteristic is not here the 100% this horizontal, we provide some slope, and this is basically called the natural regulation, and it is due to the transformer which we connect. If you remember, here it was the transformer, then we have their SVC here. So this impedance is there, so the current which is flowing here, that will be again some drop will be there, and there will be some slope here. But sometimes we have to go for another characteristic, means we have to intensely provide more slope and the loading of the line. So the regulation slope, the terminal voltage is allowed to be less in the capacitive zone and more in the, as I said, here we require the voltage less and more here. Because we require voltage is more, then we have to go for this. The perfect regulation may result in the oscillation, as I said, it's a perfect regulation here, and then it will be oscillating. Due to the poor defined operating point, that is a zero regulation. So here the operating point is not defined. Regulation, that is a droop or slope, tends to enforce the automatic load sharing between the static compensators and other voltage regulation. Due to the coupling reactance, the voltage drop is normally 10 to 20%, but the slope reactance typically between 2 to 5. So we don't want much slope. What will happen? This slope is still not desirable. So we try to go for the minimum slope that is required, so that we should not have hunting. At the same time, we can have the stable operation. To understand this, it is very easy that we can have the different load lines here. If the voltage here, the load is your increase or decrease, voltage is less, then we have to operating characteristic will be here, otherwise it will be here. If your loading is decreased, then we can go for another, and then reactive power support is required. So these all are the system voltage or load line, and these are called the natural characteristic. So we can have the natural characteristic here, that is the intersection of this. So the natural characteristic of SVC, normally the operating, we operate in this zone, this is this, and then we have the slope, and then this one. So here this is the operating zones where we have to operate our SVC. Means when voltage is more than this reference point, then we have to go for in this inductive zone. This is your capacitive zone, and this capacitive zone, if the voltage is less, then we have to provide this one. So this is your called your current voltage, that is the VI characteristic of the SVC. Now let us go for the VQ characteristic of the SVC. Means I want to draw this Q here and the voltage line here. Already we defined this IC, it is nothing but your V into your BC. So it was a linear curve. Now if I go for the Q, it is nothing but your V square into the BC. It shows that it is a square of the voltage now, the reactive power. It was current was a linear, so which were getting the linear here, now it will be the quadratic, and then we are just going to have here this characteristic like this, and then for this zone here we can again go for this type of characteristic. So here this is your this, and otherwise this. So here this quadratic, it's not linear. For this zone it is also quadratic, and we are going to get this characteristic, and this is your operating zone. So this is your VQ characteristic of this SVC. Now here another problem, that the over rating, because we are having the inductor, what is the value that we can go for the over rating? That is that transiently that we can go for this zone as well, and that is, and we can increase. So this is that margin we can go for here from there. Now let us see the StatCom characteristic. Just we saw this is your SVC. In the StatCom, what relation we are getting, this I is the constant in the both zone. Means we can maintain this IC value constant. So I can say the V, and here this is your current, this is your V. Now we can go for here, this is IC max. We can go up to that maximum, means we can vary current in the both side, and we can go for here, that is your IL max value. So this is your operating zone in the between. Here we can go for this. But again, as I said, if voltage is less, we have to operate in this capacitive zone. Here this is the capacitive, this is your inductive. So the actual characteristic is normally it will be operating here in this zone when the voltage is less, and when it is voltage is higher, it will be operating in this zone. So this hash line area will be now, this is your operating zone. This is again we have to provide the slope, and this is your. So now you can say it has the wider range, as I said in the very beginning when I was comparing in the previous lecture the SVC and STATCOM. Here you can say this zone is very small. Here we have the wider range, especially the low voltage. You can say the voltage is here low, only we have this one. Here we have this wider range. To add the practicality, here if the voltage is 0, we cannot go for the IC maximum. Normally we add another characteristic here at this end. It is not possible to maintain the IC if the voltage of the system is 0. So in that case, here we go for this characteristic, and normally we can get the characteristic like this. Here up to this very small voltage, this we can go here, we have slope here, and this is your, that is VI characteristic of, and this is your zone of operation. This is your STATCOM. So it is better, that's why this device is better than that device. Now if you are going for the reactive power, as I said, we can see the reactive power here, and now I can draw here the reactive power here. This is your Q, this is your V. Now this value, this horizontal line, that's I said the Q will be your IC into your this voltage. So it is a linear. Now we can have this characteristic here, and now this zone also we can have this and this one. So you can see this is the better here, this value is very less, this is more, this is reactive power support, and this is characteristic of STATCOM. So this STATCOM is the better in terms of dynamic range. It has a wide dynamic range, it is a better operating range, and also it has a more overload capability, means we can go for these currents more, and then it both side. Here only this side we can go for the more current, and normally we require in this capacitive zone. So this is basically the difference between the SVC and the STATCOM. Now let us see another, that is a major difference, that when I was saying that if we are going for this P delta curve, if I was telling you, if you remember this is your delta, and I said it is without compensator. If you are going to compensate, ideally here we are going to the double this. When there is no limit in the midpoint compensator, then we will achieve the P delta here, this curve. This is without compensator, this is with compensator. Now if the limiting value is hitting, means if your value for SVC is hitting, then what will happen? This is your pi by 2. As I said, here it will be like this. The characteristic will be here finally. So where it is hitting, it depends. Means here the VC max, I can say this is nothing but this is your VC max, the total VC max, how much you are achieving, and then you are getting this characteristic. However, in this STATCOM, what we are going to get, again I will compare this. This is without, means infinite limit. If your system, that's the hitting, that's the current limit is hit, what we are going to get here, we are going to get here. It is not going to 0, mind it, only the difference here is all that's going to 0, because now we are having simple inductance. The inductance is fixed, variable part is 0, and finally we have to come here. Here we are injecting, this is your, this value is IC1 max, here IC2 max, and it depends, the IC2 max is more, and then we are getting this characteristic. Now here also we can say that this device is better than this device when improving the transient stability of the system. How come? Now you can see again for one case, previous case which I was using the fault, simple one. Let's suppose this is midpoint, this is here, this is your, this is the generators, this is we are putting here our SVC or STATCOM. If you remember here, now again I can draw this P angle here. This is without compensator. If we are using compensator, what is happening? Now we can go for this much. Now our system, it was the operating, the mechanical power here it was there, and now this value is your 0. After a certain time of the fault which occurs here at this bus, it is clear, and your system will be coming here, and then this value, this area here must be equal, and this area here it is your A2. Now for the different value of the limiting value, now we can see, let us, it is a SVC. In SBC I said if your this is a heating, we are getting this or we are getting this. Now how much margin you are getting? This margin, if your this is your characteristic, which is this value is heating, then you have this margin, or you are having this margin, or you are having this margin. These are the margins. Now the same, if you will see here, what we are going to do. Now you can see this, now this, and this value is now hitting. Now you can see now this value is not 0 here, it is, we are getting this characteristic more. Now if it is more, now it is this. So this is not going to be 0, earlier it was going to be 0 here, so we are having more margin. So we can say the StatComs are better in terms of the dynamic performance than your SBC, but the StatComs are expensive compared to your SBC, and that's why this device is very popular and very simple also. It's very simple to control, very simple to manage, and already we are having all these things. If you see the time response here, the StatCom, basically time response is from 200 microseconds to 500 microsecond. This is for StatCom. However, for SBC it is from 2.5 to 5 millisecond. So this is very fast compared to the SBC as well, because we are having the control, we are having the converter based technology. Here we are the inductors. If you are switching here, you will require some time. So here this time is millisecond, so it is also very fast as well. So let us see the impact how this SBC or StatCom can improve the voltage and the system performance by improving the voltage. As I said, let us take the characteristic of any device, that is SBC or StatCom. We are having some slopes here, that is, I said that the natural slopes, or it is the non-natural slopes. Means the natural slopes means already we are having the transformer impedance is there, and that drop is just related with the VI characteristic. This is your I, this is your voltage. Now if you are having this, let's suppose your system load line is this. Now if your voltage here, the system line is reduced, if more load is increased, what will happen? If there is no compensator, it was operating here at this point, now it is coming here, and your the voltage drop is your in the system, that is this much, that is your delta V. But if you are having the characteristic, you are having some compensator, and you can have this characteristic, what will happen? Now this is your operating point, that is a operating point will be the intersection of these two curves, that is characteristic of device plus this load line or system line. Now what will happen? Only the difference here in these two is, now I can say this is your delta V. So this delta V1 is always very less than delta V, and we can say our system voltage variation is very less, and then you can say that is an improvement in your voltage profile. Same times, even though we can change these characteristics from here and there by firing the angle, and then even though we can maintain with this load line this voltage, and we can get this characteristic, and then the voltage can be also fixed to the terminal voltage. So whenever this load and voltage variation takes place, there is a possibility by changing the firing angle we can change the characteristic, and then we can maintain the terminal voltage to its rated value. Now let us see the various combination of your StatCom. Let's suppose we have the StatCom characteristic, as I said, means we have the StatCom plus we can have some fixed capacitor, means we can have the minimum rating, this margin is less, but we can add the fixed capacitor, they are very cheap. Another, we can have this StatCom plus I can say thyristor controlled reactors. We can have another several combination of this, even though we can have StatCom as well as your here TCR plus fixed capacitor we can put, and then this is plus your StatCom, that is nothing but here it is your SVC. So we can see the characteristics, means the characteristic that we can change, and we can say how it is going to be this. Now the StatCom characteristic, as I said, this is your StatCom characteristic between these shown. Here this your IC max, maximum current, that is in capacitive zone, here your IL max. Now if you are adding the FC, what happens? Now you are adding this characteristic, that is a slope here, and and so therefore this is a fixed value, so this will be subtracted here, this will be added here. Now your operating zone will be this much. What is the advantage we are getting? Most of the time, if the voltage is less, we want the reactive power support, and here you can say this area, this zone, here now we are having this final one, and this is more, and this system is better compared to complete STATCOM. Now if you are having this STATCOM plus TCR, the characteristic again here we are having this. Now this TCR is nothing but this characteristic. So what we are going, this is the variable one, so we can go from here 0 to here, so we are adding this region only, so we are having this characteristic completely. So this is your this characteristic, or we can add the STATCOM and SBC, and that will solve the purpose of your whole wide range in that area. And then we can have the fixed capacitor here, we can have the TCR as well here. What will happen? There is a possibility that we can maintain this one value with this variable. So we can go for this zone even though like this, and we can have the very wide zone of STATCOM, and then we can operate our system very smoothly. So basically this is the STATCOMs, or these devices are very, very popular to improve the power system performance, again in terms of static as well as dynamic performance. Here again I want to show you that this reactive power here, the supply is one objective, means whenever they are connected they normally feed reactive power, or they can absorb whenever required. Means the STATCOM or SBC, they will inject the reactive power at the system when the voltage is less. When the voltage is less, for example STATCOM configuration as I showed you here, this is your converter, and now this is voltage E, this is voltage V, here I, so I can say this V minus E upon X is I. If this voltage is more, then we can say it is just providing the current to this system, and therefore the leading and lagging current is decided by this one, whether this current is injected or that one we will get from here. Now, so the reactive power, they will be providing the reactive power to the system when the voltage, this voltage V is less than V naught, then they will be providing this reactive power, that is called positive generation. When this V is greater than V naught, they will absorb reactive power, and normally it is they will get from the system to maintain the voltage. So these devices in the steady state will work like a simple reactive power support devices, but their supplementary controllers can be used to improve the dynamic performance. As I saw that using these devices that we can change the transient stability limit, and at the same time we have to model their dynamics as well if you want to see the impact together along with the system dynamics. So the modeling of these devices in the dynamic is also very equally important, and normally they are modeled by the simple single order equations, and means it is a current which is here giving, in that it is a BCSC, that is a capacitive impedance is variable, and then we can go further with different time fractions. Already we saw they are very, very fast, and their dynamics can be also included in the transient, in the simulation of the SBC or STATCOM with other systems, that is a dynamics already we have defined earlier. In the total, we can suppose we are having other devices, then control coordination problem is also one of the major challenge. Means we are having the, let's suppose HVDC, we are having the controllers, that is your exciter controllers, you are having the real power controller, that is LFC loops, you are having the controller corresponding to the fax controller. So there may be possibility that these controllers will interact to each other, and they may oscillate, and system may go somewhere else, even though instead of improving the dynamic performance. So the design of controllers and their tuning is equally important, and we have to take care there in a very sophisticated and efficient way. So I can now recap with this now lecture number your 9 and 10. Here I just discussed the fax controllers. Those are only the Sun type, because the Sun type here is very simple, and it is used for the reactive power support, along with that they will improve the dynamic performance. So here we saw that some characteristic, that's as I said, the slope characteristic. Now again, sometimes some people ask that why this characteristic here, this is a VI characteristic of the StatCom, or you can say SVC. We not going for the 0 here slope, always we go for some slope here, and it is very minimum that we go for 2 to 5%. As I again said, if it is a 0% slope, then there will be the operating point is not possibly been shown. For the same voltage, it will be oscillating, hunting. So we intentionally we go for the 5%. We don't want to 2%. Means 2 to 5% we can maintain. 0% is not desirable. However, we can go for that. But in the natural characteristic, this slope is 20% because the reactance of the transformer is very high. So the I or V characteristic is related with the reactance of the transformer. So we normally go for such type of compensators that is having the slopes up to 2 to 5. We saw the performance of both StatCom and the SVC, and we found that StatComs are better than SVC in several aspects, that they will improve the transient stability better than SVC if the limits are available. They can damp out the power system oscillation efficiently compared to the SVC. They can also provide more reactive power, that is a dynamic range, compared to the SVC. Only the limitations of StatCom is that it is an expensive device compared to your SVC, that is very simple and reliable. That's why it is existing in the system from very long period. So this whole module, now I can recap this whole module. We just discussed about the load frequency control in the very basic few lectures. Then we model the power system, and after that we went for the AVR loops, that in AVR loops, that is the automatic voltage regulation of the alternators. We also saw some other devices for the reactive power sources and sinks, that is a transmission line, transformers, cables, boosting transformers, etc. They can provide some reactive power support through the system, and of course the capacitors are one. And we also saw this FETs controller, those are the shunt in the nature, that is SVC and StatComs. Here in the whole this voltage and the frequency, we saw that we can improve the power system, and that is very, very important to run the smooth, reliable and the secure power system. Thank you.